All right, so chapter 17 was called Toxic Cleanup. And the topics that we hit on here were double replacement reactions, specifically precipitation reactions, writing those out, looking at how to predict whether or not an ionic substance is soluble or insoluble in water, and stoichiometry. So just to recap the precipitation reactions. So this example here is showing us an aqueous solution of potassium chromate and an aqueous solution of barium nitrate. We're going to write out what that double replacement or precipitation reaction looks like. What this is showing us here is it's basically a reminder that, remember, ionic substances dissociate when they are dissolved in water. So even though we're writing out the aqueous potassium chromate like this, it actually looks like this in water. It splits into 2 potassium ions for every 1 chromate. We can see them floating around there. And the same thing with barium nitrate. We get 2 nitrate ions for every 1 barium. Okay? Now, when the potassium chromate and the barium nitrate react together, the double replacement reaction that happens swaps the cations. So the cations find a new anion partner, essentially. And what I like to do first is to write out what the charges of each of the ions are to start with, because those charges stay the same. They carry with them when they do the swap. So when potassium and nitrate come together, all we're doing is balancing their charges, ignoring any of the subscripts right now that tell us how many there are. Potassium's +1, nitrate's -1, so that's KNO3. And then barium is +2 and chromate is -2. So it's going to just be one of each of those to balance to 0. Now, to balance the overall equation, right, that conserves mass. And that we do by changing the coefficients in front. So placing a 2 in front of the KNO3 will balance the equation. We can only do that, though, once we write correctly the formulas for our products. Then we also have to be able to predict what the phase of each of the products are. Now, either one of them is going to be a solid, or they're both going to be aqueous, and no visible reaction is going to occur. In this case, we can see from this diagram here that the potassium and the nitrate ions are still floating around in solution, right? So that means they are still aqueous. The chromate and the barium ions have come together to form a solid, so they are the insoluble solid that forms, and we call the insoluble solid a precipitate, which is why we call these types of reactions precipitation reactions. And what we would see, as you should remember from class, when we combine the two solutions, if a solid forms, we do see the solid in the form of sort of either a cloudy change in the liquid, or sometimes it looks gelatinous, jelly-like. It's not like a typical solid that you're used to seeing, but there is some sort of observable change. Now, for select substances, you will have a table to use that will help you figure out whether or not something is soluble or insoluble. And remember, generally the way it works is these are separated based on anions that generally form soluble compounds and anions that generally form insoluble compounds. So we want to look for the anion in the formula, and then we want to see, do they exist in generally soluble compounds or insoluble compounds? And then we have to look for, are there exceptions that would basically negate that rule? So as an example, for potassium nitrate, nitrate is here, exists in the section that generally forms soluble compounds, and there are no exceptions to that. So potassium nitrate would be soluble. Barium, let's say sulfate. Sulfate is also in the top portion of the table. When we see sulfate in compounds, generally those compounds are soluble, except if the compound with sulfate contains strontium, barium, mercury, or lead, and barium would be one of those exceptions there, so that makes it soluble. All right, so that's how you would navigate the table. couple of examples we can try and walk through together. So the first one is potassium nitrate, aqueous, barium chloride, aqueous. And at any point, you can pause the video in sort of steps to see if you're going to write out the products correctly, balance it correctly, do the phases. Here are our charges that we're going to have to use to write the formulas. We're going to get barium nitrate, and we're going to get potassium chloride. We check the table. These are both aqueous, so no reaction occurs here. Remember what no reaction means. Not only do we get no visible reaction, we get no visible reaction because I have a bunch of free-floating ions separate from one another before and after I mix them together. Right? We talked about the idea of spectator ions. All of these ions would be spectator ions. There's no cation anion pair that are going to come together to strongly attract to form a solid. So no reaction occurs. We don't have to balance the equation as a result of that. Number 2, we have sodium sulfate and lead to nitrate. +1 -2, +2 -1. So we're going to get sodium nitrate and lead 2 sulfate. Sodium nitrate's aqueous, the lead 2 sulfate solid, so that's the precipitate. We're going to balance the equation, put a 2 there. And then in our last example, we have potassium hydroxide and barium nitrate. Our charges, +1 -1, +2 -1. We're going to get potassium nitrate and barium hydroxide. And both of these are aqueous. So again, another example where no reaction occurs. No need to balance the chemical equation. Now remember, balancing the chemical equation to segue to the stoichiometry piece. Balancing a chemical equation not only conserves mass, but it shows us the mole ratio. Mole ratio is the ratio in which reactants come together in a reaction and a ratio in which the products form, right? It's just like a recipe. When you follow a recipe, you have ingredients that you use and you have to combine them in a certain ratio, certain amount of cups of flour to eggs to sugar, whatever, and it's going to get you a certain number of things, a certain number of cakes or cookies or pies, whatever it is. The mole ratio is this works in the same way. So as an example, if we balance this equation 1 to 3 to 2, this is telling us that every time this reaction runs in full, is completed one sort of full run through, 1 mole of nitrogen is going to react with 3 moles of hydrogen to produce 2 moles of ammonia, 2 moles of NH3. So this is what we call our standard mole reaction, right? It's a balanced chemical equation that gives us the mole ratio. And we can answer questions with this here. So let's say that I'm going to use this recipe, right, to look at this amount of starting material, right? It's almost like we open our cupboard to see how much we have to make cookies. We open up the lab and I see that I have, if we're following this here, 3 moles of nitrogen, right? 1, 2, 3, and 6 moles of hydrogen. 1, 2, 3, 4, 5, 6. And I want to think about, well, how much could I make with this amount of reactant according to this recipe, according to this reaction? And we looked at the idea of a scale factor. A scale factor is something that we use to see, like, how many times can we run the reaction full through with the amounts that we have? So if every time this reaction runs, it uses 1 mole of nitrogen, and I have 3 moles, then I can run this reaction 3 times with this amount. So to find a scale factor, we always take what we have divided by what the reaction is going to use, one full time through. If I have 6 moles of hydrogen and each time the reaction runs it uses 3 moles of hydrogen, then I can run the reaction 2 times with just the hydrogen. The problem that we run into is with both of those amounts together, it is impossible to run the reaction 3 times through and to run the reaction 2 times through. So we are literally limited by the smallest scale factor, right? The least number of times we can run the reaction through. So we will only be able to run the reaction 2 times as a result of the hydrogen. That makes hydrogen our limiting reactant and nitrogen our excess. Limiting meaning it literally limits how far the reaction can run. It's going to run out first, so it stops the reaction from proceeding any further. The excess reactant is what we will have left over. Then we look at the idea of taking our scale factor and multiplying it through the reaction to get our scaled reaction. So that would be 2 moles of nitrogen. If it's going to scale 2 times, we'll react with 6 moles of hydrogen to produce 4 moles of NH3. So with those 2 amounts, if I combine these 2 amounts together, I can produce up to 4 moles of ammonia. 6 moles of hydrogen are going to be used. That makes sense because that was limiting, so that's going to be used completely. And then if we notice for the excess reactant, I started with 3 moles, but only 2 moles are being used. So I have 1 mole of nitrogen in excess, right, left over. If I started with 3 and the scaled reaction only used 2 of it, I have 1 mole left over. These are all sorts of questions that we should be able to answer. We can actually use the particle diagrams here to show, sort of like confirm the math that we just did. So if we follow the recipe or the mole reaction, every time 1 mole of nitrogen is used, 3 moles of hydrogen are going to be used to produce 2 moles of NH3. I'll try and draw them pyramidal because that's geometrically how they exist. The reaction can run again. 1 of those, 3 of those should get us another 2 of these. And then the reaction can't proceed anymore, right? We've exhausted the hydrogen. We've used all 6 moles. I made my 4 moles of NH3 and I have 1 mole of nitrogen left over, right? So it just confirms it there. You could stop the video now, pause it, make sure that you have everything you have on the screen. I'm going to clear this to get ready to do the last few example problems together. Because I want to run through the setup that I think you should do for every stoichiometry problem. I reiterated this in class and what I posted on Google Classroom, but I think this is the most efficient way to do it to make sure you get the answers right every time. Again, the first thing to do is to make sure you properly write out your chemical equation and then balance it. This gives you your standard mole reaction. That's the first thing we're looking for. The next thing we're looking for is the molar mass of each of these substances. So I use the periodic table to find the molar mass of each substance, and I like to just write it tiny above each of them. Now, molar mass by definition is grams per mole, grams per 1 mole of the substance. So when you find the molar mass, we're ignoring these coefficients. These coefficients come into play because I want to convert this mole reaction into a standard gram reaction. In other words, 1 mole of N2 is equal to 28 grams. 3 moles of H2 is equal to 6 grams because each mole is 2. And 2 moles of NH3 is equal to 34 grams. And we should be able to see conservation of mass at play there because the total mass of the reactant should equal the total mass of the products. Now we have everything we could possibly need to answer any sort of questions that we want here. So let's look at the first one. How many moles of nitrogen are needed to produce 18 moles of ammonia? Well, if my standard mole reaction is producing 2 moles of ammonia, but I want to produce 18, that means I need to scale that mole reaction by a factor of 9. And if I'm scaling it by a factor of 9, and I multiply through, that's telling me that 9 moles of nitrogen are going to react with 27 moles of hydrogen to produce 18 moles of ammonia. So now I go back and I look at what is the question actually asking me? How many moles of nitrogen are needed to produce 18 moles of ammonia? Well, according to my scale of the reaction, if I'm going to produce 18 moles of ammonia, I need 9 moles of nitrogen. They didn't ask about hydrogen. They could have, but I also need 27 moles of hydrogen to produce 18 moles of ammonia as well. Now, I could have taken that scale factor of 9 and multiplied it through my gram reaction, but that would have been unnecessary because they were asking me for quantities in moles, right? So we're going to see, like, it's going to be, when we think about efficient problem solving, looking at, what choices are we going to make to solve the problem in the most efficient way possible. The next question says, how many grams of ammonia will be produced if 9 moles of hydrogen react? So if 9 moles of hydrogen are reacting, let's go back to our standard mole reaction. Every time that reaction runs once, 3 moles of hydrogen are used. So if in my reaction 9 moles are going to be used, that's scaling the reaction by 3. Now I could multiply through by 3 and scale the mole reaction, but that wouldn't be a really wise choice because they're asking me for grams of ammonia. I'm going to take that scale factor and multiply my gram reaction. So 28 times 3 is 84 grams. And then we have 6 grams times 3 is 18 grams. And then we have 34 grams times 3 is 102 grams. So how many grams of ammonia will be produced if 9 moles of hydrogen react? Here's my 9 moles of hydrogen represented in grams, but that's equivalent to 9 moles, right? Each mole is 2 grams, 9 moles, 18 grams. How many grams of ammonia will be produced? 102. How many grams of hydrogen are needed to react with 10 grams of nitrogen? So let's go check out my standard gram reaction. Each time this reaction runs once, 28 grams are used. If I'm only using 10 grams of nitrogen, my scale factor, I'm scaling this down. We have to be careful, right? It's always what we have divided by what the reaction tells us. So 10 divided by 28 gets us a scale factor of 0.357. How many grams of hydrogen? So I'm going to scale my gram reaction down. 28 times 0.357. There's my 10 grams. Hydrogen, 6 times 0.357 is 2.14 grams. And then 34 times 0.357 is 12.14 grams. So how many grams of hydrogen are needed to react with 10 grams of nitrogen? 2.14 grams. And then our last question, what's the maximum number of moles of ammonia that can form when 5 moles of nitrogen and 13 moles of hydrogen are placed in a container allowed to react? So they're giving us amounts of each reactant. We have to see how each of them scale and then compare the scales. So 5 moles of nitrogen, each time my reaction runs, it uses 1 mole of nitrogen. So that's going to scale up by 5. If I have 13 moles of hydrogen, each time this reaction runs, it's using 3 moles of hydrogen. So that's scaling it by 4.33 repeating. These two reactants are not scaling the reaction the same. That means they're not combining the mole ratio. That means I have a limiting reactant and an excess reactant. My limiting reactant is the one that's going to scale it the least number of times. So the 13 moles of hydrogen is going to be my limiting reactant there. Smallest scale factor. Nitrogen is excess. I like to write that out right away just to keep my work organized. So now what I'm going to do is go through that reaction and scale it. They were asking for maximum number of moles of ammonia, so I'm going to scale the mole reaction. So 4.33 moles of nitrogen must react with 13 moles of hydrogen to produce 8.66 moles of ammonia. So My limiting reactant we answered already is hydrogen. Nitrogen was in excess. What's the maximum number of moles of ammonia that can form? It's going to be this amount, right? Because that was the amount that could form with the least scale factor. It's 8.66 moles of nitrogen, NH3, ammonia. If they asked for grams, I can use the molar mass, right? 17 grams per mole, and just convert it to grams, or I can go back and scale the gram reaction with that same scale factor. You're going to get the same answer. They didn't ask for how much excess is left over, right? They asked for which one is in excess, that's nitrogen. But if they ask for how many moles of nitrogen are in excess, I go back and I see, well, I started with 5 moles and only 4.33 moles reacted, right? So 5 minus 4.33 gets us 0.67 moles of nitrogen left over. And if we wanted how many grams of nitrogen are left over, again, you can do the whole thing with the scale the gram reaction, or because I have the 0.67 moles of nitrogen right here, and I have the molar mass of nitrogen, it's a quick conversion. Set up dimensional analysis and convert the 0.67 moles of nitrogen to grams. So I can't stress enough to practice setting up your stoichiometry with all 3 pieces here. Your mole reaction, your molar masses, and then your gram reaction, and then being able to navigate those different pieces to answer whatever stoichiometry questions can be thrown at you.